Hello everyone and welcome to another video of the video series of myself looking at companies from the quantum computing, quantum communication and quantum sensing space. In today's video we are going to look at QuantWare. So here I'm on the website of QuantWare and I'm seeing a golden object here. It says amplify readout with crescendos. Oh, sorry. And there is a contralto A. First of all, we accept the cookies. Yeah, okay, there's like a lot of products down here. And from what we can see, we already see that has to do something with the quantum computing space here, because we see here 17 qubit tunable coupler QPU, 21 qubit fixed coupler QPU, 5 qubit fixed coupler QPU, and 64 qubit fixed coupler QPU, and a TWPA. And I guess we will learn more about what this is in a second. But first of all, very cool logo. Somehow it gives me vibes of Korean letters almost, but then on the other hand, it also looks a bit like the Egyptian symbols. So very interesting for sure. So here it already says something about this product. Reach the next milestone toward large-scale error-corrected quantum computing with up to 17 flux tunable transport qubits, 24 tunable couplers, expert support and upgrade path to VIO-powered QPUs. Control-A provides a foundation for building fault-tolerant systems. Okay. So what do we have here? First of all, it says something about foundry service. So foundry, usually in the classical sense, when we talk about semiconductors, basically means that you have like for example, Intel, they have a fab, a foundry. They have a fab business where they produce their own stuff, but they might also sell it. But Intel is not, let's say, the classical candidate. The biggest foundries are like global foundries, or Samsung also has a foundry business where you can send them your designs and they create it for you. And here it says foundry services, custom designs. With QuantWare's foundry services, everyone has access to our best-in-class fabrication technology. From resonators and junctions to fully assembled QPUs, we've got you covered. So it looks like they are also producing as a service for others quantum hardware, so chips, including resonators and junctions. So here we are talking about superconducting technology. And we can also see something here. So you see these lanes here, which have this typical zigzag shape, which we know from the resonators and so on. So this is like one service that they're offering. Okay, then we have here QuantWare designs, develops and fabricates state-of-the-art superconducting quantum hardware with excellent specs and good service. Okay, here we see who's already using their services. So we see ETRI, Waterloo, University of Waterloo, and QuantRoll-Ox. Sorry. But there's also more down here. We see Alice and Bob, which is a French startup in the space of quantum technology or quantum computing. We see Leiden Institute of Physics here, so also some European players. Q-Blocks is also part of it. So we see there's quite a couple of known names also already in this list, which is, I think, for the foundry services. Then it says, making quantum hardware accessible to all. With scalable, affordable, customizable technology, we allow our customers to develop and experiment freely and create value. Contact us to find out how we can accelerate your research. So they see themselves as a facilitator and accelerator for quantum hardware research. So basically creating quantum hardware in the lab for others with these services. But also above we saw that there are some products, and I think we will learn about them in a second. Now there's something about them. Here you see the team, all very young and dynamic people, I would say. They're also hiring, okay, and then there's some partners here. So for example, Delft Circuits is mentioned here as a partner, Q-Control, which we've also seen before. And there is also other ones here like Zurich Instruments, for example. It's also funded by the European Union. And with that, let's hop back up and check out their products. So we see quite a lot of products. Basically, the products, so they have products and services. Services is the Foundry one, which we talked about before. Then there's two types of products which are advertised here, which is the QPUs, so quantum processing units, and amplifiers. The QPU is usually the chip where you put the qubits on, right? So this is like in this case, we are talking about superconductive technology. So you will have your Josephson junctions, which will be part of the for example, transmon qubit. And then you have several transmon qubits, which are coupled to each other via these couplers. And then by this, you basically create a system of multiple qubits. And now you also need amplifiers, because usually you don't want to send like super strong signals down there, down into the cryostat where the QPU is sitting, for several reasons. First of all, you're trying to manipulate quantum systems. So you have to be very careful. You have to apply small signals, but you also receive small signals from these systems. And then also you have to make sure that the thermal load down at the chip is of course very low. So you cannot send 15 watts of energy down to the chip, because if you do that, it will heat up the whole system. So these cryostats, they also have a limited amount of cooling power at this very low stage, where you are like 15 millikelvins at 15 millikelvin temperature. So what is it? 0.015 Celsius, about the absolute zero. So extremely cold temperatures, and therefore you have the requirement to operate at extremely low signals, at extremely small signals, and for that you need those amplifiers. And you actually want to put those amplifiers into your cryostat, into the cold stages of the system, because of the fact that you want to keep the thermal noise in your system very low. Like if you have an amplifier at room temperature, you can have it operate very well, but of course, when you go down into the cryostat, you can also use the cold temperature, and you can make sure that your amplifier operates with less noise if you cool it down. And I guess we will learn more about these in a second. Now we see a very nice chip. So here's, I think, what like a typical superconductive chip looks like. So you can see here the different connectors around here, where you would usually, like, I guess, put your bonding pads, where you connect the wires of your chip to where you connect the wires of the system to the chip in a way. Then you see those let's say metal areas here, which I think are usually used for flux trapping. I'm not an expert when it comes to all of this, so don't believe me everything I'm saying here. And then I guess these would be like the typical cells where you have the qubits, and then you have these couplers between the different qubits, which you can also see here. So this is the 17 qubit tunable coupler QPU, Contralto A. There's also the D version, which has 25 qubits. And then we see here that we have the ETRI, so QuantWare's Contralto D QPU, and the TWPA with their high qubit coherence and effective circuit design in terms of qubit frequencies, coupling parameters, and connectivity were essential in enabling us to accelerate both hardware and software development, significantly advancing our universal fault-tolerant quantum computing research at ETRI. Then we see here a 12-line QPU. So by the way, usually the processor, so the silicon chip which has the superconductors on it, will probably be below this cap here, so below this metal lid with the logo on it. Then what you have is you have these areas here on the side where the contacts to the metal contacts to the qubits lead out to, and there you have like bigger pads that are used for bonding usually. So you put a wire on there, and then you put a wire somewhere else, for example, on a chip carrier, on a pad. And then you can connect to the chip carrier from the outside with some pins. And those pins, they are usually then connected to, for example, these lines here. So you see here, there are like a couple of plugs there. These are coaxial plugs, which you can probably use for, they are usually for high frequencies. So you can play with gigahertz frequencies when you operate on those. And they would then be connected, and you see something here like a pattern on here. They are connected into this area here, and then you have the chip carrier, which is connecting to the chip via the bonding wires inside of that. And yeah, then we see here some more customer feedback on that. Then we have the TNOR-D, the world's largest commercial available quantum processor powered by QuantWare's VIO platform with 64 fully controllable qubits, enabling scale with reduced crosstalk. Then we have here the amplifiers, I guess. So it says a near quantum limited traveling wave parametric amplifier. So that's what a TWPA is, a traveling wave parametric amplifier, enabling ultra low noise microwave detection for qubit readout and more. So yeah, as I said, like it says near quantum limited. So that's the limit, the noise limit dictated by quantum mechanics. It says ultra low noise here. It's for microwave frequencies, which is also something quite specific. So you need something that can operate on quite high frequencies. So you need high mobilities in those types of amplifiers. So this is like very specialized equipment here, which is being used by the University of Waterloo, for example. And then we see here where these devices go. So this is like the lowest stage of your fridge, of your cryostat. On the back side of this golden plate, which you see here, that's like on the other side. Usually that's where your QPU would sit. So it probably sits somewhere here. And then you see you have these very rigid RF cables. So these are usually like stainless steel coaxial connectors. I'm not even sure if you could call them cables, because they're like more like pipes, I would say, so that they don't absorb or that they don't start shaking because of vibration in the system or anything. So, and these are then connected here to these amplifiers at the very lowest temperature stage. And then you can see like the signal goes up here to the next stage, and then probably there's some filters also in the system at higher stages, and that's how the signal flow in such a system is set up. Then we here see again like the foundry services, this time also with a nice logo on the chip, very cool. You see some probing station here, so you usually have like a microscope. This is probably like, I'm not sure, I would guess it's like a room temperature probe station. So you take the chip which you produce in the fab, and now you might want to test if your processes have actually been working out and if everything's working from an electrical point of view the way it's supposed to. So you can already test that at room temperature, and what you usually do is you have the chip, you put it on this stage here, and then you have those needles, and you can actually move them by changing those screws here, by turning those screws. You can lift them up, move them to the sides, whatever, and then you can place them down. And now you place them on these pads here, where later on the bonding wires go. But now you can place them here, and you can connect some measurement equipment, and then you can do some pre-characterization, usually at room temperature, but there are also some stages where you can actually cool it down. So sometimes there's like a cooling mechanism below here, and then you can cool it down to, for example, liquid nitrogen temperature or whatever. So that's usually a very good indication already, and it makes it easier to actually check for the quality, because you don't have to assemble everything, put it in the cryostat, cool down the whole system, which usually takes, I don't know, a day or two to actually reach the very base temperature, to then realize that something was off in your fabrication process, right? So that's also a very useful tool, and that's also why you probably want to make use of such a fab service, because it comes with all of this equipment that is actually necessary to do this type of testing. Okay, so now we've seen that. There's also some resources here which include news articles, then like scientific articles, I guess, and there's a glossary. On the news side of things, so we see here there's like the 1st of July. So this video is being recorded in end of July, beginning of August. So I think this is like pretty much up to date. It says here there's like a 1 million, I guess, funding or project, which they have gotten. And there's some other stuff here, like company update, QuantWare partners with Nano Vacuum to accelerate the advent of scalable quantum computers in Australia and New Zealand. So there's a lot of stuff happening. And with that, let's see what else we have here. There is also a partners tab. That's interesting. So here we see like the quantum technology stack, right? It starts with the QPU down here, which includes the qubit design. That's like the silicon. That's like the Josephson junctions, the couplers, the capacitors that you actually need to build the qubit. Then on top, we have the qubit chip, where you have multiple of these qubits assembled in a way, and then maybe also coupled with each other. Then we have the VIO. On top of that goes the packaging, shielding, and signal conditioning. So this is like what we've seen before, like how those chips are being mounted in the metal casing. Then this metal casing also used as a shield. And then there's the signal conditioning, which includes the amplifiers, right? So this is all counted here as the QPU. Then on top of that, you have the cryogenic system and signal delivery. We see some partners here. So there's like Form Factor, leading manufacturer for cryogenic test and measurement systems. Maybell Quantum is on a mission to deliver the world's best tools to solve the toughest quantum challenges. And then we also on top of that have Delft Circuits, which provides the ultimate solution to connecting qubits to room temperature electronics. So this is like the whole electronic side of things. On top of that, we have the quantum control hardware. So we see like Zurich instruments, which are making measurement devices that usually sit in your lab at room temperature, but also control devices, so they can control the signals that are going down to your qubits. There's also other ones like Tabor Electronics, Quantum Machines, CQC, and QBlocks here. Then we also have on the other side quantum networking hardware. So there is like QFox, I would guess, is a quantum transduction company that is building the world's first quantum modem. So that's like quantum internet, I guess. Then we have the quantum control infrastructure. This is now on the software side of things. So we have the hardware, which is producing the signal, and we have the software, which is controlling what signal goes in, what comes out, and so on. So there we see Q control, and then there's Quantrol Ox, and then we have the quantum error correction architecture, which I think there's nothing here yet. And then there's applications on top of that, which is also again with Q control in this case. So I think that's a very nice idea to actually highlight like the partner ecosystem and the people that you are working with in such a way by putting it together on this whole quantum computing stack here, or the quantum technology stack. There's also some information about resellers. This is like, I guess, regional players. You have probably like for the different continents, for the different areas, different resellers here in this partner network. There's also a tab about events. So the next one that is coming up seems to be the SQA conference in Delft in August. So that's, then there's the IEEE in August/September. So, and there's also stuff which they've been doing before. Very good. Let's end this little video with a little look at the About page. So making quantum hardware available to all. This is the mission, I guess, of the company. So this is very much also in line what we are doing here, right? They are democratizing the hardware. We want to democratize the knowledge. By the way, if you want to learn more about those companies, and if you want to Keep learning about the quantum ecosystem. Make sure to subscribe to this YouTube channel to not miss out on another video. And now back to the website. So there's QuantWare launched in July 2021 with the singular ambition to accelerate the usefulness of the quantum computer while democratizing hardware and expanding the field. QuantWare works on the quickest path to useful quantum computation based on a foundation of world-class expertise in scaling up superconducting QPUs. Achieving useful quantum computation is a huge challenge and one we cannot do alone. We are a collaborative company working with the best-in-class companies and experts on complementary solutions. We are always on the lookout for new partnerships. And that's what we've seen before, right? There's this partner page highlighting the whole ecosystem of independent partners. So you don't have like one company that is selling you the whole system, but here you have like really the ecosystem, kind of the supply chain of quantum computing in a partner network that they are creating. There's something about the board of directors and the scientific advisors here. Then there is some more about the investors and the team down here. Very nice. So you can actually see everyone who's contributing in the company. Everyone seems very happy. Also, by the way, very cool that they have these branded t-shirts. I also like the fact that all of the photos, they have the same look and feel to them. So it's not like you have different color schemes, different filters, whatever. They're all in grayscale, all with a very neutral background. I think that looks very professional also. And yeah, it's a long list. Everyone's LinkedIn profile is also linked to this little text about them. Of course, like due to the time constraints, we can't go through all of them. And then there's also like some hiring opportunities here. Very good. With that, I would say we call it a video. Never forget to stay hydrated and see you in the next one. Bye-bye.